Okay, let's unpack this. You sent over this fascinating paper, really foundational stuff, about improving neural networks.
Yeah, that's the one.
Specifically, this technique they introduced called dropout.
That's right. It's improving neural networks by preventing co-adaptation of feature detectors. Came out of the University of Toronto, and, well, G.E. Hinton is on there, a name most people will recognize.
For sure. So this paper, that's our main source for this deep dive. And the mission really is to cut through the jargon, figure out what dropout is, why they thought it would work, and importantly, what impact they actually showed it had.
Yeah, exactly. It's one of those techniques that sounds, well, almost too simple when you first hear it.
Right.
But the effect it had, at least according to this paper, was pretty significant.
Okay, so where do we start? I guess with the problem they were trying to fix.
Yeah, that makes sense. The paper really starts by tackling a classic problem in machine learning, especially with big networks and maybe not, tons of data. Overfitting.
Overfitting.
Right.
That's when your model gets really, really good at the specific examples you trained it on, but then it just falls flat when it sees new data, like it didn't learn the general idea.
Exactly. It's like memorizing the practice questions perfectly, but not grasping the concepts, so you fail the real test.
Okay.
And in neural network terms, they explain this happens because the hidden units, the parts doing the feature detection, they become too reliant on other specific hidden units.
Ah, these co-adaptations they talk about in the title.
Precisely those.
Yeah.
These units start working together in these really complex, intricate ways that are specific only to the training data.
So they work great on the training set.
Yeah, they minimize error there. But those specific collaborations, those co-adaptations, they aren't general enough. They're brittle when faced with slightly different data.
The network kind of gets stuck.
Right. Stuck in these hyper-specialized modes.
Okay, so that's the problem. These fragile, codependent feature detectors causing overfitting. And this is where it gets interesting, because their solution, dropout, it feels almost backward.
It really does, doesn't it?
Yeah.
The basic idea is, well, during the training phase, for every single training example you show the network,
Yeah.
you randomly pick some of the hidden units, just turn them off.
Yeah.
Omit them.
On.
This is one example.
Yep.
They don't contribute to the calculation going forward, and they don't get updated during the backward pass, the learning step.
So like maybe half the neurons in a layer are just sitting there doing nothing on any given training step.
That's the idea.
Yeah.
The paper suggests a probability of 0.5, so yeah, about 50% for the hidden layers, maybe a different rate for input units. Often you keep more of those.
Okay.
But the key is it's random for each training case.
Yeah.
A different set of units gets dropped each time.
And the logic is, by randomly knocking units out, you stop any one unit from depending too heavily on any other specific unit, because that other unit might just vanish next time.
You got it. That's the core intuition. Each unit has to learn features that are useful on their own, or at least useful in combination with a random selection of other units.
Like constantly changing teammates in a game.
Exactly. You can't just rely on passing to your one favorite player. You got to be able to work with whoever's actually on the field with you at that moment. Makes everyone more versatile.
Okay, that makes intuitive sense for breaking those brittle co-adaptations.
Right.
But the paper also gives another way to think about it, right? A second perspective.
Yes, they do. And it's also pretty powerful. They frame dropout as being a really efficient method for doing model averaging.
Model averaging, like training a whole bunch of different networks and averaging their answers.
Right, which is a known way to get better generalization, make the model more robust. But it's super expensive computationally. You have to train, tens or hundreds of separate models.
And keep them all around for predictions.
Yeah. So dropout, by randomly disabling units for each training case, is kind of like implicitly training a huge number of different networks all at once.
How so?
Well, every time you drop different units, you're essentially training a unique, thinned version of the network. But crucially, all these exponentially many thin networks share weights for the units that happen to be active.
Ah, so you get the benefit of averaging over maybe, 2 to the power of however many units.
Exactly. A massive ensemble.
But you only actually train and store the parameters for one underlying network structure.
Precisely. It's a very clever way to get the regularization benefits of averaging this vast ensemble without the massive computational overhead.
Okay, that's neat. A computational trick with a strong theoretical justification. So how does the training actually work? Is it just standard gradient descent, but you randomly zero out activations?
It uses standard stochastic gradient descent, usually on mini batches,
Yeah.
But they add a specific twist regarding the weights. Instead of a typical L2 penalty on all the weights, which just pushes everything towards zero.
Right, weight decay.
They impose an upper limit, a constraint, on the L2 norm,
Yeah.
basically the length of the vector of incoming weights for each individual hidden unit.
So just the weights feeding into a specific neuron.
Yes. For each hidden unit, they look at all the weights coming into it from the previous layer. If a weight update would make the total squared length of that weight vector go above some maximum value C,
Yeah.
they just scale all those incoming weights down proportionally so the length is exactly C. They renormalize it.
Huh. Why that specific constraint? Why limit the incoming weights per neuron like that?
Their argument is that this prevents the weights from exploding, from becoming arbitrarily large, even if you get really big gradients sometimes.
Okay.
And because you have the safety net, it allows them to use a much higher initial learning rate. They can start learning more aggressively and then decay the rate over time. They suggest this lets the network explore the possible weight configurations more thoroughly, potentially finding better solutions than methods that have to start with tiny learning rates.
Got it. So dropout for the units, this per unit incoming weight norm constraint, and aggressive learning rates. That's the training picture. What about when you're done training? You want to make a prediction on new data? You can't keep dropping units randomly then, surely.
Yo, absolutely not. That would give you a different answer every time you ran the same input through.
Right. Why is he?
So at test time, you use what they call the mean network. You use a full network with all the hidden units active, no dropping out.
Okay, all units are present.
But, and this is the key adjustment, you take all the outgoing weights from those hidden units, the weights connecting them to the next layer, and you multiply them by the dropout probability you used during training. So typically, you have them.
Have the outgoing weights. Why half? Seems a bit random.
It's not random, it's about compensating. During training, if you used a 0.5 dropout probability, any given hidden unit was only active about half the time, right? So the signal it was sending to the next layer was, on average, only half of what it could have been if it were always active.
I see.
At test time, the unit is always active, so its output would be roughly double what the next layer got used to seeing during training. Having the outgoing weight brings its contribution back down to that expected level from training.
Okay, so it balances out the expected activation level. Makes sense. And this whole mean network approach, using all units but scaling the weights, how well does it work compared to, say, actually averaging many random dropout masks?
They argue it works remarkably well. It gives performance very similar to explicitly averaging over a huge number of dropout networks, but it's way, way more efficient. Just one forward pass.
Nice.
And they point out some nice theoretical properties, too. For networks with a softmax output layer, which is common for classification, this mean network approximation is actually equivalent to taking the geometric mean of the probability distributions predicted by all the possible 2n thin networks.
The geometric mean, right.
And for regression tasks, using this mean network is guaranteed to give a squared error that's less than or equal to the average squared error you'd get from averaging the predictions of all those individual dropout networks.
So it's computationally cheap and theoretically sound. Okay, the big question then. Did it actually work? Did it deliver on this promise in their experiments? Let's look at those benchmarks you mentioned.
Yeah, they tested across a range of standard tasks. First up, MS, the handwritten digits. Using a standard feed-forward net, Dropout cut the error significantly. Their baseline without Dropout, similar to prior work, got about 160 errors. With 50% hidden dropout and that L2 norm constraint, they got down to around 130 errors. Then they also tried dropping out some of the input pixels, about 20%.
Dropping the input too, okay.
And that got them down to 110 errors. They also showed it helped when fine-tuning other kinds of networks, like deep belief nets pre-trained on MST.
And they mentioned something about visualizations.
Right. They visualized the features learned by the first hidden layer. Without dropout, the features looked kind of messy, complex. With dropout, they looked much cleaner, more like individual strokes or edge detectors, more interpretable, maybe more fundamental building blocks.
Interesting. Suggests it's learning something more general. Okay,
Hey.
what about timid speech recognition?
On Timidity, Dropout also gave solid improvements. It reduced the frame classification error rate, and more importantly, boosted the overall recognition rate. They went from 22.7% error down to 19.7%.
Which was good at the time.
They claimed it was state-of-the-art for methods that didn't use speaker adaptation. Plus, they noted it made the models less sensitive to the network size, and crucially, they didn't need to use early stopping anymore.
Getting rid of early stopping is handy. Less fiddling with validation sets.
Exactly, just train for longer.
Okay, moving to images. CIFAR 10. Small color images.
Right. Here they used a convolutional neural network, a CNN. Their baseline CNN got 16.6% error. By adding 50% dropout only to the final hidden layer, the fully connected one before the output.
Just the last layer.
Yeah, just there. They reduced the error to 15.6%. So an improvement, maybe not as dramatic as MNIST, perhaps because CNNs already have some regularization built in with weight sharing and pooling, but still better.
Okay. And the monster data set, ImageNet. Thousands of classes, millions of images.
ImageNet's the real stress test, especially for large models. They used a big, deep CNN. Their baseline, without dropout, achieved a 48.6% top one error rate.
Okay.
Then they added 50% dropout to the fully connected layers, the ones near the top, which have tons of parameters and are really prone to overfitting.
Right, those dense layers.
And with dropout, the error rate dropped to 42.4%.
Wow, that's a jump, over 6 percentage points lower.
Yeah, a really significant improvement. And they explicitly say in the paper that dropout is essential to get good performance from these large, fully connected layers. Without it, those layers just overfit badly and couldn't generalize.
So it really enabled training those higher capacity parts of the network effectively. Any other domains? Text.
Yep, they looked at Reuters, a document classification task. Using a standard feed-forward network, the baseline error was 31.05%. With dropout, it fell to 29.62%.
Consistent improvement again.
Yeah, and again, they noted the learning curves were smoother and they didn't need early stopping. So the pattern is pretty clear across these different tasks. Images, speech, text, and different network types feed forward, CNNs.
Dropout just consistently seems to help the models generalize better.
That's the takeaway from their empirical results, definitely. Especially useful for large models that might otherwise overfit the training data.
You mentioned the 0.5 probability was common, but they looked at variations.
They did briefly. They suggested that for the input layer, a higher retention probability, maybe keeping 80% or 90% of the inputs, is often better. You don't want to discard too much raw information right at the start.
Makes sense.
And they speculated about adapting the dropout rate, maybe per unit, or even making it dependent on the input itself, kind of like a precursor to ideas like attention or mixture of experts, where the network learns which parts to focus on.
Interesting. And they also tried to connect dropout to other existing ideas in machine learning, didn't they?
Yes, they positioned it relative to a few things. It's much simpler computationally than full Bayesian model averaging, even though it achieves a similar effect of averaging over many models.
Right.
They call it an extreme form of bagging. Bagging is where you train multiple models on different random subsets of the data. Dropout is like that, but extreme, because every training case effectively uses a different model, the thin network.
But with shared parameters.
Exactly. And that parameter sharing across all these implicit models acts as a very strong regularizer. Stronger, they argue, than standard weight decay penalties.
Okay. And what was that comparison to naive Bayes? That seemed interesting.
Yeah, that's a neat point. Naive Bayes classifiers work surprisingly well sometimes, especially with limited data, even though they make a usually false assumption that all the input features are independent of each other given the class label.
Right, the naive assumption.
The reason it often works is that by assuming independence, it avoids learning complex, potentially spurious correlations or co-adaptations between features from the training data. It focuses on the individual contribution of each feature.
Ah, so it doesn't overfit those feature interactions.
Exactly. And dropout, by constantly breaking up the groups of hidden units that are active, similarly prevents the network from relying too heavily on complex co-adaptations between its internal features. It forces features to be useful more independently, which helps generalization, especially when data is scarce relative to model size.
So it achieves a similar kind of robustness by preventing over-specialization on feature interactions. Okay, now, there was this really unexpected connection they made at the end of the paper, something totally outside of ML.
Ah, yeah. That's the analogy to biology. It's quite thought-provoking.
What was it again? Something about sex?
Exactly. They referenced the theory about why sexual reproduction evolved and persists. The idea is that sex, by shuffling genes from two parents, constantly breaks up combinations of genes that have become highly co-adapted.
So like a set of genes that work really well together to perform some function in a specific way.
Precisely. Sex potentially breaks that set apart. This forces biological functions to be achievable through multiple, perhaps less optimized but more varied combinations of genes. It prevents the species from getting stuck with one super-specialized genetic toolkit that works perfectly now but might be disastrous if the environment changes.
It prevents evolutionary overfitting to the current environment.
That's the analogy. Just like sex breaks up co-adapted genes to make organisms more robust and adaptable to changing environments, Dropout breaks up co-adapted feature detectors in a neural network.
To make the network more robust and adaptable to new data.
Exactly. Preventing computational overfitting to the training data. Both mechanisms promote robustness, but discouraging over-reliance on specific partnerships, whether genetic or computational.
That is a really cool parallel, finding a similar principle at work in evolution and in training an artificial neural network.
It does make you wonder, doesn't it, about potentially deeper, more fundamental principles of adaptation and robustness that might apply across complex systems, natural or artificial.
Absolutely. So, wrapping this up then, this paper introduced Dropout as really a deceptively simple idea,
Yeah, just randomly ignore units during training.
but with profound effects. It helps neural networks generalize dramatically better by stopping these internal feature detectors from becoming too reliant on each other, preventing those complex co-adaptations.
And it acts like this super efficient form of model averaging, implicitly training and combining a vast number of networks, which provides powerful regularization.
Leading to, as they showed, state-of-the-art results back then on major benchmarks in vision, speech, and text, particularly enabling much deeper networks.
It really became a standard tool in the deep learning toolkit for a long time.
And that final connection to evolution, it just leaves you thinking, right, about these underlying principles of building robust, adaptable systems. What other echoes of natural design might we find, or perhaps should we look for, in the way we build intelligent machines?
It's a fascinating question. Makes you wonder what other biological or physical principles might translate effectively into better machine learning.